Dear colleagues, thank you very much for the invitation to take part in this conference. The topic of today's talk is traffic sign recognition for visually impaired pedestrians in Kyrgyzstan. Two-keypoint SIFT BRISK descriptor with CameraX. The authors are Dr. Ayman Dr. Dmytro, Dr. Andrey and Nurlan Shaidulayev. Authors work for University of Central Asia, Kyrgyzstan, and Kryvyi National University, Ukraine. The motivation of this work is to simplify the integration of the visually impaired people into social activities via the assistance of their spatial cognition. Frankly, I always ask the question, why so many people want to support the visually impaired, but so few actually do it? My answer is that all of us should do as much as we can to support people with disabilities. In this study, the traffic sign recognition system was developed to assist the spatial cognition and ability of visually impaired pedestrians in Kyrgyzstan. The system employs a two-keypoint binary descriptor that implements the BRISK algorithm to find sampling patterns on the image. Pairs of keypoints are localized using the SIFT method. The developed Java Android mobile application implements the SIFT and BRISK approaches in real time on Android CameraX using AdaBoost classifiers and multithreading. With a knowledge base of 86 sampling patterns, the execution time is 0.1 second for the example with the traffic sign crosswalk left. In experiments conducted at distance 1.5 to 3.5 meters in the city of Naryn, Kyrgyzstan, the present SIFT BRISK detector demonstrates a true negative rate of 100% and a true positive rate close to 100%. Smartphone Blackview BV6600 Pro and Doogee S96 Pro achieved 100% and 75% respectively at 3.5 meters. What SIFT and BRISK algorithms are and how they are employed in this study. So, SIFT stands for Scale Invariant Feature Transform. It identifies distinctive local features or keypoints in the image. It is invariant to changes in scale, rotation, and elimination. And in this study, keypoints serve as anchor points. BRISK stands for Binary Robust Invariant Scalable Keypoints. It is used for feature detection and description in computer vision and image processing. And in this study, once keypoints is detected by SIFT method, which generates a descriptor. Then BRISK matches sample pattern, if any. This slide shows a diagram of two keypoint SIFT detector and BRISK descriptor with CameraX Android API. So the first step is the generation of all keypoints available on the current image. The second step is the design of all available descriptors based on some case of the key points. Then we can go to the stage of the real-life experiment, and in this real-life experiment we also pass two previous stages. Okay, so first of all we capture the image on camera smartphone. We found that any up-to-date camera smartphone can handle this task. So after capturing the image, we convert the color image to the grayscale. And then we are looking for key points on the grayscale image we received at the previous step. Okay, so at this point, when we apply SIFT approach, we are looking for 400 key points. And we're trying to find these key points starting from the center of the image. Then we split these key points into pairs, and we are trying to design the descriptor based on BRISK approach. And if the developed descriptor is somehow close to the sample pattern based on the Hamming distance, we say that we found the the sample pattern on the current image. This slide represents the architecture of the proposed image matching. So it is very close to the previous one. So we are talking about third stage, where we implement actually the image matching algorithm. So we start with image capturing, then we downsample the image with bilinear filtering, and also we convert color image to the grayscale one. Then we find a maximum 400 key points based on SIFT approach. Then we select pairs of key points. Based on these pairs, we build the two keypoint descriptors using BRISK approach, and then based on the Hamming distance, we're trying to find the sample pattern in the image matching stage. Kyrgyzstan has over 200 traffic signs, but only 13 are related to pedestrians. And among the 13, we group crosswalk left, crosswalk right, and zebra crossing into one side crosswalk. And if we're talking about emergency exit left to right, also we group it into one side emergency exit. This slide represents flowcharts of the key points localization with the SIFT method and the image design with the BRISK method on the left, and the image matching algorithm on the right. Please pay attention that building the descriptor and at the same time image matching using Hamming distance and AdaBoost classifiers are done in parallel. We could achieve low execution time on Android smartphones based on the speed-up techniques in our Java Android application. So if we're talking about grayscale representation of the color image, so here we use 8 parallel computational threads to speed up this conversion. And if we're talking about calculation of difference of Gaussian images, we need to use 4 parallel computational threads. So for localization of key points in third, second, first, and fourth, third, and second scales, we use 2 parallel computational threads. And also for the image matching, we apply 5 AdaBoost classifiers. Also, they speed up our Java Android application. Real-life experiments showed the true positive rate is 100% for 2 smartphones, Doogee S96 Pro and Blackview BV6600 on the distance up to 3 meters. And then we have a reduction of this rate. Anyway, true negative rate is 100% for all experiments we did in the Naryn city. In other words, we don't have wrong recognitions in our experiments. This slide shows the example of the screenshot. Original image taken by the smartphone Doogee S96 Pro at cloudy weather, and the grayscale image with key points. Also, we have this scheme how we find key points. Please pay attention that we start from the center of the image. Thank you very much for your attention. Do you have any questions or comments? Okay, bye.